In this video, we're going to talk about magnitudes of vectors, how to calculate the magnitude. We're going to talk about unit vectors. These are special vectors that have length 1. And we're going to talk about angles associated with vectors. So let's take a look. All right, magnitude. The magnitude is the length of the vector. All right. Now, how do we denote that mathematically? Well, we denote it using this notation right here, double bars. If we surround the vector with double bars, we're talking about the magnitude. So the vector, remember, is an object with a magnitude and a direction. In component form, it's given by two components. The magnitude is just going to be a number. Right? It's just going to be a single number that represents the length of that vector. Okay. So here's a theorem that tells us how to compute the magnitude of a vector. So if you have a vector of the form v1, v2, so these are the components, then you can use those components to compute the magnitude. And these are in the Cartesian coordinate system, the one we talked about in the previous video, x and y. And this is how you compute the magnitude. It's just the square root of the sum of the squares of the components. All right, so why is this? Can we prove this theorem? Well, let's try it. What's the proof of this theorem? Well, imagine that we had a vector, right? So let's just draw an arbitrary vector here. That's our vector v. And we want to compute its length. Well, there's a hint here in that we saw that the formula comes from the components. So let's think about those components. One component is the extent to which the vector points in the horizontal x direction. That's v1. The other component is the extent to which the vector points in the vertical y direction. That's v2. And so if I draw this picture like this, I see I have a triangle, and it's a right triangle. And what we're after here is the length of the vector. We're after the size of the hypotenuse of this triangle. Well, we have the size of the legs, so we know how to do this, right? Pythagorean theorem. So we know that the magnitude of the vector, that's this thing that we're after here, is given by the square root of the sum of the squares of the sides, right? So it's just follows from the Pythagorean theorem, and that's exactly where they get this formula. So a very quick proof of that theorem. All right, let's go ahead and apply it to an example. Let's find the magnitude of this vector with components -2, 3. Okay, so, well, very simple. We just apply the theorem. If I want to find the magnitude of v here, I'm just going to take the square root of -2 squared plus 3 squared. Right, let's see what we get here. Get the square root of 4 plus 9. That's the square root of 13. If I could simplify that radical, I would, but this is in simplest form, so it's already reduced as far as it can go. That is the final answer. That is the magnitude of the vector. It's as simple as that. Just an application of the Pythagorean theorem. Okay. Now what we want to talk about is unit vectors. These are vectors whose magnitude is exactly 1. All right, so we just have to make sure the magnitude is 1. Let's look at an example here. Find the unit vector in the same direction as this vector. Okay, well, how are we going to do this? Well, if you remember what we said in the last video, we talked about what happens when we look at algebra of vectors, right? And one of the things we talked about was scalar multiplication. If I multiply the vector by a number, what happens? Well, we mentioned that if it's a positive number, the direction of the vector does not change. All that happens is that we change the magnitude. Now, what we want is we want the magnitude to end up being exactly 1, but we want it to have the same direction. So what I'm looking for here is a positive number to multiply this vector by so that the resulting magnitude is 1. Let's look at what happens when we multiply an arbitrary vector times a positive number. All right, so let's let C be a positive number. So I'll just write C is greater than 0. Okay, what happens if I take C and multiply it by the vector V? Well, we talked in the last video how to do this, right? I'm going to take, this is C times the vector V1, V2, right? These are the components of the vector V. And we said that I do this just by multiplying each component by that number C. Okay, so that's what CV is. So what's the magnitude of CV? Well, from our theorem before, we know that this is the sum, it's the square root of the sum of the squares of the components. So this is going to be the square root of this stuff. Well, let's see what we can do here. Look at this. C squared is a common factor. So let's factor it out. Look at this. I've got a positive number squared under a square root as a factor. Well, I can always pull that out by taking the square root of it. And what is this? This is just the magnitude of V. So what we've shown here is that multiplying by a positive number gives us, positive number C just gives us C times the magnitude. Now, what are we after? We want to make this vector have length 1. So we want the resulting magnitude, this thing, or equivalently this thing, to equal 1. So the question is, what number do I need C to be to ensure that this quantity down here is equal to 1? Well, I just need it to be 1 over the magnitude of V. This will equal 1 if C is equal to 1 over the magnitude of V. So that's the trick. That's how we're going to make this into a unit vector. So we're going to compute the magnitude of this, take 1 over that, and then multiply it by this. So let's do it. Well, we've already computed the magnitude earlier in this video. We found that the magnitude of V was equal to the square root of 13. If we hadn't already computed that, we'd have to compute it now. So we know from what we just showed that 1 over root 13 times V will be a unit vector. So that's what we want. Well, what is this? Well, if I'm going to multiply this by 1 over root 13, I'm just going to pull that 1 over root 13 inside, multiply by each of the components. So this is going to be the vector there we go. That's guaranteed to have length 1. Now, if you don't believe me, go ahead and check it. Use the formula for magnitude, the Pythagorean theorem, and check it. Verify that this thing does indeed have length 1. You'll see that it does. All right, so that's how we find a unit vector pointing in the direction of a vector. All right. Finally, let's talk about angles. Sometimes we want to know the angle that a vector is pointing. Angle with respect to what? What are we measuring our angle against? Well, we're going to measure our angle against the x-axis. Although you could use the same tricks that we're using here against any line, right? But let's say it's for the x-axis. So let's find the angle that the vector -2, 3 makes with the x-axis. So let's just draw a picture of what's going on here, just to make sure that we're not thinking about things the wrong way. All right, so here's our vector v. Here's the x-axis. Okay. Now I want to measure my angle from the positive x-axis, and maybe I should have written that up here. All right, so we're going to do the positive x-axis. So we're going to be measuring this angle right here. That's the angle we're after. Now, what we're going to do, though, is we're going to first find this angle over here. Call that phi. We're after the angle theta, but we're going to start by finding the angle phi. How do I find the angle phi? Well, let's use the same trick we used earlier. Let's make a triangle. Let's drop a line down like this. That's going to be V2, right? And then we're going to drop a line going this way. That's going to be V1, right? V1, V2 makes V. Well, what are V1 and V2? This distance, because that's a -2, this distance is just 2, right? And then this distance is 3. So how do I find this angle phi in terms of these side lengths? Well, if you think about trig, and pause the video if you're not sure about it, think about it. See if you can come up with what we're about to do next. What trig rule would I use to find phi given these values? Okay, you should have come up with tangent. We know that tangent phi is equal to 3/2. Well, if I solve this for phi, I know that phi is tan inverse, or another way to write that is arctan of 3/2. All right. Now, that's not the angle I'm after. I want the angle with the positive x-axis. I actually want theta. How do I get theta from this? Well, we know that the theta plus phi is 180 degrees, or let's keep things in radians. Unless told otherwise, always do work in radians. 180 degrees is the same as pi radians. So what that means is that theta is pi minus this quantity. So our angle that we're after is pi minus arctan of 3/2. Now, if you work this out, if you were asked to find a decimal, keep in mind we're working in radians. So make sure that whatever computational item, calculator, app you're using is set to radians here. All right? And if you do that, I worked it out ahead of time over here. You should find that arctan of 3/2 is about 0.9828, right? And so this thing, if I take 3.14159 minus that, you should be getting 2.1588. So check this on your own. Make sure that you're computing this the right way so that when we do this in the future, you're on the right track. Don't go to degrees unless you're asked to go to degrees. Always keep things in radians. Okay. Now for the last example today, I want to look at another way to find a unit vector. We're going to do the same problem we did before, but we're going to do it slightly differently. Find the unit vector in the same direction as v. Okay, we already did this, but I'm going to show you another trick. All right. So our vector v, let's draw a picture of it here, looks like this. Now, let's put it in standard position. So that means that the axes, here's our x-axis, and here's our y-axis, are right here. I want to find a unit vector in the same direction. So what I'm going to do here is I'm going to draw a unit circle. The circle with radius 1. And we're going to put that right here. So I can see now what my unit vector is. My unit vector is this guy right here. That's my unit vector. So how do I get this vector? Well, here's the trick. I know that any point on the unit circle of radius 1, any point on here is determined by this angle. Right? You should remember this from trig. The coordinates of this point are, pause the video and think about it. All right, you got it? Yeah, this point has coordinates cosine theta, sine theta. That's the coordinates of this point. Well, that point, the coordinates of this point form the components of this vector because the vector's in standard position. And since we already found the theta in the previous problem, we found theta to be about 2.1588. I've rounded here, that's approximate. I know that the unit vector that I'm after, this guy, let's call it u for unit vector, can be written as cosine 2.1588 sine 2.1588. There we are. And that's it. That's the answer. Now, it looks different than the answer we wrote down before. Let's see if we have it here. The answer I wrote down before was this. But if you check it, go ahead and check it on a calculator, you'll see that this and this are exactly the same. So two different approaches to finding unit vectors. If you happen to be able to find the angle, or you're given the angle, this is a really slick way to do it. If you only have the components of the vector, maybe the other way is a slicker way to do it. But either way will get you the answer. Make sure you practice both ways. They're both very useful. All right, so that's it. Magnitudes, unit vectors, and angles.